Good day everyone, my name is Khatib Sharbini, alongside with me.
Hello, my name is Faris Razik. We will be presenting our experiment on the inverse square law and linear absorption coefficient of gamma rays.
Let's get started.
Our presentation is organized into 10 key sections which are outlined in the table of contents. Let's begin. First, we will cover safety precautions. Safety is always our top priority when conducting any activity of experiment. Firstly, please handle the radioactive source with tweezers and never handle them or expose any part of the body in front of it. Second, keep the source in its container except when it is being used and store it whenever it is not in use. Our next section focuses on the objective. This experiment aims to study the interaction of gamma ray with matter. Second, to determine the linear absorption coefficient of the aluminium and lead absorber. And lastly, to verify the inverse square law of radiation. Here are the tools and resources we use to achieve our objectives, such as null scintillator, portable gamma ray spectrometer cyclone rate comp, radioactive source cesium-137, lead absorber, aluminium absorbers, tweezers, and lead shielding.
Introductions. When gamma rays pass through a materials, the intensity decreases due to absorptions. This decrease depends on the material's thickness and properties. Mathematically, the relationship is expressed as I equals to I naught times exponent to the power of negative mu x, where mu is the linear absorption coefficient and x is the material's thickness. The half-value layer, HVL, is the thickness required to reduce the intensity by half. It can be calculated using the formula x half equals to 0.693 over mu. This helps us to understand the shielding effectiveness of different materials. However, as gamma rays travel in homogeneous space, their intensities are attenuated, where the intensity of radiation decreases from a point sources as the inverse square of distance d. The formula is intensity is inversely proportional to 1 over 4 pi d squared.
Next, we will discuss the procedure. These are the steps we follow to complete the task or experiment. Part 1. Linear absorption coefficient. Begin by setting up the experiment. Place the cesium-137 radioactive source and the cyclone detector at a fixed distance of 100 cm. Turn on the cyclone detector and measure the background radiation with the source shield by a lid cover. Record the background count rate. Place the thinnest lead absorber in the holder at a distance of 20 cm from the radioactive source. Open the lid shield of the source and measure the gamma count rate. Record the value of after waiting for 1 minute. Repeat the measurement for additional lead absorber thicknesses by replacing the plates and ensuring the source is shielded during each replacement. Repeat the same step using aluminium absorber of varying thicknesses. Calculate and record the average count rate for each thicknesses. Part 2. Inverse square law. Position the cyclone detector at a starting distance of 100 cm from the cesium-137 source. Open the lid shield of the source and measure the gamma count rate at this distance. Record the value after waiting for 1 minute. Move the detector closer to the source, reducing the distance in step, and repeat the measurement at each distance. Plot the corrected count rate against the distance to analyze the relationship and verify the inverse square law.
Result of data. Table 1 is about counting rate with lead absorber. The data that we obtain while conducting the experiment is filled in the table below. Note that the background counting rate that we obtain is 194 CPS. Also note that corrected count rate equals to mean count rate minus background count rate. This is the plotted graph of corrected count rate versus lead absorber thickness on semi-logarithmic graph. This is the least square analysis and uncertainty. In our experiment, the least square method is used to fit a linear trend to semi-logarithmic plots, allowing precise determination of linear absorption coefficients and assessing how well the data aligns with the theoretical models. For lead absorber, the value of gradient m that we obtain from the experiment is negative 5.1 exponent negative 5 plus minus 0.132 exponent negative 5. Y-intercept that we obtain is 3.25 plus minus 0.011. Table 2. Table 2 is about counting rate with aluminium absorber. The density thickness of aluminium absorber that we use in this experiment is quite different compared to lead absorber. You can see our data as in the table below. This is the graph of corrected count rate versus aluminium absorber thickness on semi-logarithmic graph. The least square analysis and uncertainty for aluminium absorber, the value of gradient M that we obtain is negative 3.76 exponent negative 5 plus minus 0.287 exponent negative 5. For y-intercept C, we obtain is 3.24 plus minus 0.001. To find the equation representing the linear graph of corrected count rate against absorber density thickness on a semi-logarithmic graph. From the equation that I picked from the earlier introduction, ln I over I naught is equals to negative mu x. After the derivation, we will get the linear equations will become log base 10 I equals to negative mu over density ln 10 times density x plus log base 10 I naught. This align with y equals to mx plus c, where y equals to log I, m equals to negative mu over density ln 10, x equals to density x, and c equals to log I naught. This is the calculation about finding the linear absorption coefficient mu and calculate the half value thickness of both absorber. For aluminium absorber, the gradient M that we obtain from the graph is 3.76 exponent negative 5. Note that the density of aluminium is equals to 2700 kg M negative 3. After we insert the value of gradient and density of aluminium, we will get that the absorption coefficient mu is 0.234 cm negative 1. Then we insert the value of mu inside the half value thickness equations, and we will get the answer of x half equals to 2.96 cm. Same as lead absorber, with the density of lead is equals to 11,348 kg per meter cube, with the gradient of lead absorber equals to negative 5.10 exponent negative 5, we will get the answer of mu is equals to 1.333 cm negative 1. By using the equation for half value thickness, we will get the answer of x half equals to 0.520 cm. To find the theoretical value for linear absorption coefficient mu, we will note that the energy of gamma for 137 CS is 662 keV. After finding the constant theoretical value of mass attenuation coefficient mu over density at 600 keV for lead and aluminium, alongside with the density of lead and aluminium, then we will get the value of linear absorption coefficient mu for lead is 1.416 cm negative 1 and aluminium is 0.211 cm negative 1. Finally, the moment of truth, percentage of error of linear absorption coefficient for lead and aluminium absorber. For lead absorber, after the calculation of theoretical value minus experimental value over theoretical value times 100%, the percentage of error for lead absorber is 5.86%, while for aluminium absorber is 10.9%.
This is result from table 3 of inverse square law experiment. The table below is a log of our experiment result of source detected distance and corrected count rate. This is plotted graph of log corrected count rate versus log distance on graph. So the linear equation for the graph would be log n is equal to negative 0.4241 log SDD plus 4.1116. Next, this is the least square and least and uncertainty. Thus, the value of gradient is negative 0.42 plus minus 0.05 and the y-intercept is 4.11 plus minus 0.092. To analyze and prove that the counting rate around the radiation source is inversely proportional to the square of the distance, from the graph, the linear equation is log n is equal to negative 0.4241 log SDD plus 4.1116. From the equation that we derive is log n is equal to negative 2 log SDD plus log C over 4 pi Then that is the comparison. So the result does not prove the inverse square law because negative 0.4241 is far from the value negative 2. However, the experiment shows that the counting rate around the radiation source is inversely proportional to the distance since the gradient of the graph is negative.
Discussions. This experiment shows how different materials can block gamma rays based on their properties. Lead, with a high linear absorption coefficient, is more efficient at attenuating gamma rays compared to aluminium. This is due to its high density and atomic number, which allow it to absorb radiation more efficiently. The experiment also highlights the concept of the half-value layer HVL, which represent the thickness of materials needed to reduce the gamma ray intensity by half. Lead has a smaller HVL, meaning it requires less thickness to block radiation compared to aluminium. In the second part, the inverse square law was tested. The results show that as the distance from the radiation source increased, the intensity decreased. However, there were deviations from the theoretical value, likely due to the decay of Ca-137 source and measurement limitations. Overall, the finding emphasized the importance of choosing the right materials for radiation shielding and maintaining a safe distance from radioactive source. In conclusions, matter can block radiations with different efficiency. In this experiment, the lead has mu of 1.416 cm -1 and half-value layer of 0.520 cm. However, aluminium has mu of 0.211 cm -1 and half-value layer of 2.96 cm. Besides, this experiment showed that the intensity of the radiations will decrease when the distance from the radioactive source is increased. So that's all from us. Thank you.